Hey guys, it's me again. It's a bit late, so yeah. I'm gonna make this quick. So this is the problem set 4 for micro. Okay, I'm gonna go over the questions. Hopefully this will be helpful to you guys, and yeah, let's get started. So first of all, for question 1, you can see here. Well, if we zoom in a little bit more here, hopefully that should be more visible. 1 unit of output can be produced by any of the following combinations. So we have 3 points here. And we know that these combinations of points produce 1 unit of output. It's asking us to construct the isoquant for q equals 1. And knowing that these points can make q equals 1, we can essentially just plot a curve that says this. This is going to be the equivalent of this one here. If I can expand it. Yeah. It's going to be like this. Okay, so we have our points here, A, B, and C, or Z1, Z2, Z3 if you wanted. And we're going to just draw we're going to draw an isoquant between them, and that's going to be the deal. You don't have to, I don't think you really need to necessarily calculate it, you just need to construct it. If it said calculate, then I would calculate it, but it said construct, so I'm using this. Okay, then for the next one, assuming constant returns, construct the isoquant for Q2. If we're assuming constant returns, then we're assuming the shape of the isoquant is maintained. So we're essentially, if we look here, just going to double each point. So it just becomes a larger isoquant, as you can sort of see here. Okay? This is all you really have to represent, I believe. So that's the case. Okay? So, in the technique Z4 equal to 0.25, 0.5 were available, would it be included in your answer to part A? It would not be included because, as you can see, that point lies here, and that technology isn't efficient because it lies within the feasible set, not on the boundary. So it's not going to be feasible because it's not as efficient of a technology as, for example, A would be. So no, we wouldn't include that. Okay, number 2. So number 1 I thought was quite easy. Number 2. Do the isoquants stuck to the axes? Okay, so it says, okay, first of all, affirm as the technology Q is equal to, and there's the production function here, so you have Z1 alpha, Z2 beta, plus gamma, Z3 plus delta, where Z1, Z2, Z3 are its inputs, and non-negative constants alpha, beta, gamma, delta, and Q is output. Do the isoquants touch the axis? Well, yes, actually, they do. So, to determine if something touches the axis, we need to set every variable to 0 except 1. Okay, and only in one case does this actually work. Okay, if I set Z1 and Z2 to 0, then Z3 can find it itself. But if I set Z1 and Z3 to 0, then the first time becomes 0 as well, so that doesn't work. So the only time it works is the intersection of Z3 with its own axis, okay? Which you can find. So if we eliminate this variable over here, as you can, and I've sort of shown it here, but I've shown it quickly. If we eliminate ZA, ZB, we're left with Q is equal to gamma Z3 plus delta, which simplifies to Q minus delta over gamma equal to Z3. And that is where the isoquants will intersect the Z3 axis. That's the deal. Okay, what are the MRTSs between the three products? The MRTSs are marginal rates of technical substitution, and they're calculated as the partial derivative of one input over the partial derivative of another. So you can just sort of see that there. If we do this for all of them, we end up with, for example, so for, So I'm going to do a sample. So the MRTS of 1, 2 is going to be equivalent to this, pretty much. And if we look at our function there, we can say that the first one there is going to be alpha Z1 alpha minus 1, Z2 beta, and then this one is going to be beta Z1 alpha, Z2 beta minus 1. And if we divide these, we're left with Z1 alpha minus 1, Z2 beta, and then put this over beta, Z1 alpha, Z2 beta minus 1. Okay, we can cancel this one out and just sort of make this into 1, and then the same thing goes here. This goes into 1. So we are left with alpha Yeah, alpha Z2, beta Z1. And that is our marginal rate of technical substitution for 1 and 2. Now you can repeat this. The ones with 3 are much easier because the third input just resolves to gamma. So that's pretty easy. Okay? You can see them in more detail over here. Okay. Now, for what values of the constant is the technology homogeneous? Now, I'm sure you guys remember what homogeneity is. So if we calculate for homogeneity, we can see that if we're putting that here in Z1 and Z2, we're going to come out with lambda to the power of A plus B, alpha plus beta. But if we put it in front of Z3, it's just going to be lambda equals 1. Okay, so the point at which it is homogeneous, okay, necessarily, is the point where you have alpha plus beta equals 1, because then that makes the lambda of the first term equal to the lambda of the second term. It's also the case that delta has to be 0 in this case, because if delta wasn't 0, then we would have an addition to it, and that would make it non-homogeneous. So remember, alpha plus beta equals 1 and delta equals 0, and that's essentially it. Now for homotheticity, it's a bit tricky. Basically, homotheticity means that if we scale up the inputs, a new isoquant is generated, but it also has a different definition, which is that all the MRTSs have a homogeneity of 0. Okay? So, yeah, all the MRTSs are homogeneous to degree 0. So if we actually test this, so for example, so the MRTS for 1, 2 is equal to, as we've established, this. But if we add in the lambda here for these, well, maybe just like that, lambda, alright, then we can just sort of cancel them out because they're just cancelling each other out. So that means, necessarily, because there's lambdas on both sides that they just cancel out, that the homogeneity degree is 0. Okay? It's the same thing for all the other MRTSs. I can't really speak, sorry. Yeah, so for example, if we did it with the MRTS for 1 and 3, which is defined as, it's defined as Z1 alpha minus 1 Z2 beta over gamma. If we do this for that, then we can see that if we put it within Z1 and Z2, we end up with a lambda of alpha minus 1 and then an alpha of beta. So alpha minus 1, alpha of beta. Okay, and then you have alpha Z1, alpha minus 1, Z2 beta. Actually, can you see that behind my face? There we go. Over gamma. So in order for this to be homogeneous of degree 0, this has to equal sort of, well, not 0, it has to just equal 1, basically. No, wait, does it? Yeah, it does have to equal 1, which means the power has to equal 0. So if the power has to equal 0, then alpha minus 1 plus beta equals 0, or as our previous constraint stated, alpha plus beta equals 1. Okay? So it still works for that. It's homothetic for this constraint, alpha plus beta equals 1. Okay, good. Now for E, it's a bit trickier. Okay? Suppose the input prices are A, B, and C for the three products. We want to find the cheapest cost of producing Q units using only the third input, using Q units only the first two inputs, and asking when is it optimal not to use all the inputs. Okay, so first of all, the cheapest cost of using the third input. So yeah, actually, how we would do this is that we would go about finding our conditional input demand functions in this case, which is a much more complicated process. But first of all, we would need to find the first order conditions. The first order conditions are defined as essentially just, So for example, for any given cost level, I think it's represented in the book as W1, you do lambda, and then Z1. So this would be a first order condition. So for C, for input 3, because the cost is C, so we're going to put C here, and we're using Z3, we're going to do lambda, and then we're going to derive with respect to Z3, which in our case just gives us gamma. So this is a constant here, okay? But the problem is, when we're normally doing this question, we normally have to substitute in. Actually, I will probably show you if I can bring up Moodle really quick. Yeah, we go. One moment. Oh, right. Let me see here. Where was it? What am I doing? Yeah. It should be in the cost minimization section. Is it in cost minimization? I think it is. In perfect competition. Is it in cost minimization? Let's check. Yeah, here it is. Yeah, cost minimization. So we have minimizing this subject, we have to derive the first order conditions, and then once we find those, we can find the conditional input demand functions from this. I'll show you in more detail for the next one because it's more complete. But functionally, the idea is that because this contains none of the variables, we can't really use it. So what we're going to do is we're just going to use our slimmed down production function, which is that if we derive with respect to Z3, we just get Q is equal to gamma Z3 plus delta, which we can just find the optimal value of by rearranging. So Z3 star, or the cost minimizing value to produce Z3, is going to be Q minus delta over gamma. And that's going to be the answer there. All right, just rearranging it. Okay, for 1 and 2, it's going to be different. Okay, so first of all, we need to find the first order conditions. So as we defined earlier, it's going to be our cost times the lambda is equal to lambda times the partial derivative for, oh god, I'm getting my z's wrong. That's going to be the case, okay? And for each of these, this is going to be lambda is times to alpha z1 alpha minus 1 z2 beta. And then for b, we have got that equal to this expression, essentially, which is going to be equal to, what is it going to be equal to? Yeah, it's going to be equal to beta, I'm just reading my own stuff. It's going to be, no, it's going to be equal to lambda beta z1 alpha z2 beta minus 1. So that's going to be the case there. So now this is the point of using the FOCs, is that we divide these two. Okay, so we have A over B, which is going to be these two over each other. Okay, so we're going to use alpha, and then we're going to have, well, we're going to have lambda, pardon me, lambda alpha z1 alpha minus 1 z2 beta, and then we have over lambda beta z1 alpha z2 beta minus 1. Okay, so that is necessarily our sort of constraint, where we've included A, B, Z1, and Z2. Now, what we do from this, the point of having this, okay, is that we can find expressions for Z1 in terms of Z2, and expressions for Z2 in terms of Z1. So, if we were, for example, well, actually, hold on, give me a sec. Well, actually, first of all, let's cancel this out, because this is a bit more complicated. We can essentially simplify this down to, well, we can cancel these out, the lambdas, and we can make, because we did this last time, we can sort of rearrange, and we get, what is it? Yeah. We get Z2 beta. Did that work? I'm just checking my work in here. Must have done it right. No, I'm right here, yeah. And beta Z1, yeah, because that just cancels. So it's 1, 1, yeah, there we go. Okay, so we are left with this. Now we can rearrange for Z1 and Z2. Okay, if we do that, we get Z1 is, I'm just simplifying here, I'm not going to go over the entire thing, but if you were to do this, you get beta alpha, no, not beta, B alpha. There's a difficult thing here where you've got beta, B, A and B, but you also have alpha and beta, so it's a bit annoying. But you get this for Z1, essentially. That's going to be A, beta. That's going to be Z1. Then for Z2, you're going to get, A, beta, Z1, B, alpha. Sort of just the inverse, basically. Okay, now, if you were to actually put these into the production function that was slimmed down with just 0, 1, and 2, which would be something like Z1 alpha, Z2 beta, delta, that's essentially going to be it. We've just removed the Z3. If we put these in place of things, so for example, if I was to find the conditional input demand function for Z1, I would replace Z2 with this expression. So I would just have Z1. And if I was going to find the conditional input demand for Z2, I'd replace Z1 with this expression. And you can see I've sort of done that here. Okay. I'm just going to put these in just to show you like what to do. So for example, if I'm finding the conditional input demand function for Z1, let's start with that. I'm going to replace the Z2. So it's going to be this, Z1, alpha, and then I'm going to replace Z2, but it's the power of beta, plus delta, and I'm going to replace that Z2 with A beta Z1 and B alpha, okay? So now you have an expression in terms of Q and Z1, okay? And now what you're going to do here is you're going to rearrange for Z1, and then you'll get the conditional input demand function, which, if you have the patience for it, is going to be, remember the star here, it's going to end up as Q minus delta 1 over alpha plus beta. And then this whole expression, this mess, excluding the Z1, it's going to be this to the power of, I think it's beta over, beta over alpha plus beta. And that's going to be it. And you're essentially just going to get the inverse for Z2, okay? But fundamentally, that's how you kind of do it. You're going to find, you find the first order conditions, you divide them, you come up with an expression for this, you're going to get an expression for Z1 and Z2 in terms of the other, you sub them in, and then you get the conditional input demand function. And, okay, the conditional input demand function, this value is going to be our cost minimizing production. Okay, so if this is cost minimizing production, then we only need to times this by the cost, and we're done. So the absolute perfect, the minimum cost, well, I'll get back to the question. Yeah. The cheapest cost of producing Q units of input is going to be A, Z, because this is the cost of Z1, A, and then the conditional input demand function of Z1, plus B and the conditional input demand function of Z2. And that is equal to sort of just this, if you sort of look down here. I'll put the notes in the description, just so you guys can read in more detail, but that's going to be equal to this. Okay. For number 3, the firms in a perfectly competitive industry have the cost function of CQ is equal to 324 plus 8Q plus 4Q squared. Determine when the firms experience increasing, decreasing, and constant returns to scale. So this is a homogeneity problem. So decreasing returns to scale? I wrote decreasing, but I think I meant constant there. Right. So for a constant returns to scale to be true, we know that this must be the case. Okay, so we're going to make something that looks like that. So 324 lambda, so I'm doing the first one here, 324 lambda plus 8 lambda q plus 4 lambda q squared is equal to, then we have 324 plus 8 lambda q plus 4 lambda squared q squared. So first of all, eliminating the 8 lambda q from both of them, okay, we're left with 324 lambda plus 4 lambda q squared equals 324 plus 4 lambda squared q squared. Then we can rearrange. We're going to end up with, so let's put it 4 lambda q squared minus 4 lambda squared q squared. And then over here we have 324 minus 324 lambda. You could actually take a 1 minus lambda out of all of these. So this becomes 4q squared lambda 1 minus lambda. And if you, no, not q, it becomes this. And you can sort of calculate that if you want as well. And then this one becomes 324 1 minus lambda. We take out the lambdas. We're left with this expression. We divide by 4. We can get q squared lambda is equal to 81. Okay? And that constraint provides, oh god, that constraint essentially says this constraint holds when the production function is going to have a constant return to the scale. The cost function is a constant return to the scale. So this is the case, okay? If we repeat this for increasing returns to the scale, okay, the case is that, yeah, for increasing returns to the scale, it's going to be larger than in the case where it's going to be that. So it's basically going to be the same. I can repeat it for increasing returns to the scale. So, yeah, so 324, where is it? Yeah, 324 lambda. Is that the case? Yeah. Yeah, 324 lambda plus 8. I'll go through this quickly because I'm tired. It's like 5:30 in the morning. I've not stayed up. I just fell asleep and then I woke back up and thought, hey, might as well do the video. So, kind of a weird night for me. Changing. Okay, first of all, can't be an equality thing there. It has to be larger than 324 plus 8 lambda q plus 4 q squared lambda. Same thing. Moving it over. So we have 4 lambda q squared minus 4 squared lambda q is larger than 324 minus 324 lambda. And then we're just going to basically do the same thing as we did last time, leaving us with 4 lambda q squared, I believe. Yeah, which is going to be larger than 324 is the deal. And then, yeah, so if we rearrange, it's going to be smaller than, is it going to be smaller than, what did I mess up here? Yeah. Well, I think you guys get the idea. It's just going to be the same thing, where you get just 81 instead. I need to replace these. Give me a sec. I think I messed up here. And then it would be the same thing for decreasing returns to scale, at least in my books. So there's that. Okay. Now for the next bit, short run and long run supply curves. Now I look back at my notes for this, and it turns out that short run supply is just marginal cost, and supply curves. There we go. And then the long run supply curves are just average cost. Okay. So we know how to calculate marginal cost. We just derive with respect to Q. So it's going to be 8 plus 8Q, which is going to be equal to the short run supply curve. And then to get average cost, we just divide by Q. So it's going to be 324 over Q plus 8 plus 4Q, which is going to be the long run supply curve. Okay? So we've got that. And that's literally just it. Find the industry's short run and long run supply curves, assuming the industry contains 80 firms. Basically, all we do is we just times these equations by 80 each. So we're going to get we're going to get 640 plus 640Q. And then we're going to get, for this one, it's going to be defined times the by, yeah. So this is going to be, let me just do SR, SC, market. Let's just use the subscript M to denote market. And then for the next one, it's just going to be, I think it was just 2000, like this, basically. It's basically just times by 80. It's all fun. It's all good. And this is going to be equal to the long run supply curve market. So if current demand is existing at this for the market, I'm assuming, are firms entering or exiting the industry? So what I sort of interpreted this as is that how much profit is each firm making? Because it's perfectly competitive, okay? So how much is each firm making in terms of profit in the actual market? Okay, so first of all, what we can do is we can get a demand function that works for every firm, which means we're going to have to divide this by 80. This is going to give us a demand function of about 20 minus, I think it was 5 over 4. 5 over 4 P equals Q. All right. Now, for revenue, okay, we know it's price times Q, right? But yeah, it's going to be, hold on, what did I get here? Yeah, we want things in terms of Q instead, because it's just going to make it easier for us to calculate later with respect to Q. We can't really calculate with respect to price because Our cost function is in terms of Q, so we should probably make our demand in terms of Q. So rearranging this, we get just 2 is equal to Q plus 5 over 4P. Then you just get, instead of that, it's going to be 20 minus Q equals 5 over 4P. And then we get just 4 over 5, 20 minus Q equals P. Okay? And then that times by Q is going to be equal to this times by Q. So it's going to be the equivalent of, 4 over 5 times 20 is 16, so 16Q. And then 4 over 5, yeah, we'll just make that the same, and that's going to be 4 over 5 Q squared, which is equal to the revenue. So that's the revenue function, yeah? So that's going to be the revenue for each firm, pretty much, okay? And then the cost for each firm, we know that the long-run average cost, long-run cost function is going to be, we've specified it earlier. We specified it as, oh god, can I scroll up? No? Not at all? Not possible for me? Yeah, we've determined, okay, well, we saw earlier that the one for individual firms, the long-run supply curve is going to be this. So we're going to minus that from our revenue, and then we're going to get, that's essentially going to be, because this is average revenue, you can sort of think of it as AR. So we can say average profit is equal to the average revenue minus the average cost, which in our case is going to be 16Q minus 4 over 5 Q squared minus, yeah, let me see here, minus 324Q minus 8 minus 4Q. Okay, so there's that. Okay, then we can just take away these two from each other, and we're just left with 12Q up front. This makes it a little easier on us. Okay, so now, how do we now just work this out? So the point is that in a perfectly competitive market, firms will produce where their marginal cost equals their average cost. So to determine the quantity we're going to put in here, we're just going to say, okay, so what happens when marginal cost equals average cost? Okay, which is 8Q is equal to 324Q plus 8 plus 4Q. Cancelling the 8s out, taking away 4Q, this 324Q. It's basically going to be the same thing before, 324. Q squared is equal to 81, because we obviously can't have a negative quantity. Q is equal to 9. We're going to, oh dear lord, Q is equal to 9. We're going to put this back into here, Q is equal to 9. And if we actually put Q is equal to 9, it resolves to about, yeah, I think it's minus, yeah, it's minus 0.8 profit per firm. Okay? That is the deal. And because it's minus profit per firm, firms are going to be pulling out of the market because they're not making enough profit. And because it's perfectly competitive, we know that every firm is making roughly a negative profit. So we know that firms are going to be pulling out until there's, sufficient conditions in the market where firms can just sort of stay. But yeah, that's question 3. Now question 4, I think a lot of people thought it was more complicated than it was, but I've tried to make it simple for you guys. So if we assume sort of constant returns to the scale, we're just assuming output scales 1-to-1 with input, right? So we basically, if we're making an inequality, okay, so think of it like this. If I was to scale, so think of, for example, this relationship. I don't even know what it is. But if A, B, and Q all scale equally, they all have constant returns to scale, this inequality is never violated. So I think that's what it's getting at, rather than anything else specific. Okay, so let's say, so for quantity 1, because it says here, a firm produces goods 1 and 2 using goods 3, 4, and 5 as inputs. The production function of one good, unit I, which is 1 or 2, requires at least a ij units of unit good j, which is 3, 4, 5. Assuming constant returns to scale, how much of resource j will be needed to produce q1 units of good 1? Okay? So we can define it as an inequality, I feel, because I don't think you can give like an exact answer. This is far too vague to have an exact answer, so I've done it as an inequality instead. So I've basically done, say I wanted to produce Q1 units, and I know I need A units of good J. So I'm going to put 1 here, and then good J units, okay? So that's the units of Q1. Now I know that I can't exceed my revenue when this is essentially the cost of production, if you want to sort of think about it like that. But we're also obviously going to be producing good 2 alongside this, so we're going to have this. So they're both going to be producing with the goods 3, 4, and 5 in terms of J. But we know that this has to be underneath the valid amount of basically like revenue for this level. So I'm going to say it's underneath the revenue level of just given for each input. So this is the revenue level for Q1 and Q2. So it's just going to be this. So this is my basically constraint, okay, that says that, okay, the total cost of production has to be underneath the total revenue gained from the entire thing. And that's what I'm just trying to say, that the resource, how much of resource J will be produced is, well, how much of it will be needed is exactly the amount that satisfies this inequality here, such that this is basically such that it's technologically feasible to produce this. Okay, so that's what I'm essentially saying. For B, what we sort of want to think about is that, okay, what if I repeated this for the other 3? Okay, what if that was possible? And I've sort of given you an example here where I've created 3 restrictions and I've sort of just shown in the feasible set. So imagine, if you would, that if you had 3 restrictions, all with their different kinds of things, they would all have these sort of different lines here. This sort of acts as an inequality, a graphical inequality. And if you were using a graphical inequality, you can sort of shade in a region where your feasibility works. And if we have multiple of these overlaying each other, so for example, if I had one for input 3, one for input 4, one for input 5, if I graph all these out, they can create this area where they all intersect called the feasible set, which is going to be the technologically feasible area which is available to us. So that's going to be the case there, where if we have the given values of the good 3, good 4, and good 5, we can create a technologically feasible outputs, which is going to be the areas where the feasible set lies, basically. Okay, I think that's everything. I'm really tired, so I'm just going to go back to sleep. That's going to be fun. Hopefully you guys found this somewhat useful. I think I got through it quicker than I thought, which is nice. But yeah, alright. See ya. Bye. Have a nice day, night, whatever. Alright, bye.